buffer capacity and buffer index. So in very simple words, buffer capacity tells us about how much of acid or base we can add to our buffer before it change its pH. So and in a proper definition, we can say the capacity of a buffer solution is a measure of its efficiency in resisting the change in pH upon addition of acid or base. Alright. If while making the buffer solution, if we have added a higher concentration of acid or base, then the buffer capacity of that solution, that buffer solution will be high. And if the concentration of acid and base is low, then the buffer capacity will be low. Alright, and this capacity is mathematically measured in terms of buffer index and denoted by beta. So beta is buffer index and it is the ratio of amount of strong acid or base added in expressing number of moles divided by changing pH value of that buffer solution. So beta is equal to delta B divided by delta pH, where delta B is quantity of acid or base in gram equivalents per liter added to buffer solution. Now if we see an example of acetic acid and sodium acetate, these two combined form a buffer acid, and acetic acid being a weak acid dissociates partially into acetate and proton, while sodium acetate being a salt dissociates completely into acetate and Na positive. Alright, now let's say while preparing this buffer solution, we have taken 0.4 mole of acetic acid and 0.8 molar sodium acetate. And if we have to find out the pH of this buffer solution, we will be using Henderson-Haselbalch equation. Alright, that is equal to pH equal to pKa minus log of acid divided by salt. This pKa is required to be calculated, and the Ka value of acetic acid is this. Ka is equal to 1.8 into 10 raised to power minus 5 mole. So if you have to calculate the pK, you have to take minus log of Ka. So the value is 4.7447. So this is the pK value, and we already know the concentration of acid and salt. So we will put all these three things in the formula, and after calculation the pH obtained is 5.0457. Now if we add 0.03 moles of NaOH to 1 liter of solution, we are adding 0.03 molar NaOH solution to 1 liter of the solution, what we will see, this NaOH on addition to the solution will immediately break down into its ions, and the reason because it's a strong base. So it will only be present in the form of Na positive and OH negative. Since it's a buffer solution, so it will try to counter the addition of OH negative. So this OH negative will react with CH3COH. This on reaction will give us water molecule and acetate. So what is happening? The OH negative produced here gets converted to water, and there is no OH negative because of NaOH. That will change the pH. So we'll see on addition of NaOH how much change in our pH is happening. Let's see. Since this is consuming acetic acid, we know the molarity of NaOH, that is concentration of NaOH, that is 0.03 molar. So, and because 100% dissociation is happening here, so the concentration of OH negative is 0.03 molar. Now this 0.03, you can see 1 mole of OH negative is reacting with 1 mole of CH3COH. Therefore, the amount of CH3COH consumed here is also equal to 0.03 molar. Alright, so what is happening from the initial concentration of acetic acid, this much amount is being consumed in neutralizing OH negative. So we will write now the concentration of acetic acid will change from 0.4 molar minus 0.03 molar equal to 0.37 molar. So the new concentration of acetic acid is 0.37 molar. Similarly, since acetate ion is being formed, so the concentration of salt will be increased 0.8 molar plus 0.03 molar. So the new concentration is 0.83 molar. Now again, putting these values in the buffer equation, we will get a new pH, that is 5.0956. So we can see how much our pH is changing here, 5.0457. So 994. So this much pH is changing when we are adding a very strong base NaOH with a concentration 0.03 molar. And here we have taken the same buffer of acetic acid and sodium acetate with a concentration of acid as 0.4 molar and that of salt as 0.8 molar. But if in this case we have changed the concentration to 0.04 molar for acid and 0.08 molar for salt. Now if we calculate the pH, we will get the same pH because the ratio of acid and salt concentration is same. Alright, so this pH is same as the earlier one. Now we'll see the difference. Earlier also we had added 0.03 molar NaOH when our concentration was higher. Now we have taken a lower concentration of our acid in case of buffer, and we are adding the same amount of base, having the same concentration. Now let's see what happens. How much change in pH happens. You are taking acetic acid and the concentration of acetic acid is being reduced due to the formation of OH negative ions on decomposition of NaOH. This OH negative will react with acetic acid, hence reducing its concentration by 0.03 molar. So the resultant concentration of acetic acid is 0.01 molar. Now the concentration of acetate ion will increase by the same amount, that is 0.03 molar. So it will become 0.11 molar. Now let's calculate the pH. The ratio here has been changed. Now on calculation you get a pH 5.7861, and if you see the difference between this and this pH, it comes out to be 0.7404. So when we earlier discussed, the higher the concentration of acid or base in the buffer solution, the buffer capacity will be higher. So when we had a higher concentration, the change in buffer was very small. So the buffer capacity of this buffer is higher as compared to the buffer solution prepared by a lower concentration of acid, and the change in pH is much more higher as compared to this one. So this explains the lower concentration of acid and base in the buffer solution results in the lower buffer capacity.